Happy Wednesday, everyone. Here we are, ready for our live stream. This is Chem Help ASAP. Hope you guys are doing well today. So this week I thought, since we're at the beginning of summer and I know students are either just starting summer school or maybe are getting ready to start summer school, that it might be a good time to just do some math review of just the different math skills that you will need for a general chemistry class. Now, this is general chemistry. This includes high school chemistry, whether you're taking your first year of chemistry or whether you're taking AP chemistry. But these math skills are also useful if you're taking a general chemistry course in college as well. So we're going to start with the really easy stuff. We're going to do some algebraic work. We're going to solve for X. And then we'll get on to things that just are a little more complex. And hopefully, again, this is mostly review for you. And I hope you enjoy the live stream. Okay, so let's get started. All right, so again, I want to start with the easy stuff first. So we're going to just start with solving linear equations. So these equations just have one variable. We're just solving for X, but oftentimes, I know if your math skills are a little rusty, even just these simple things, you need a little bit of a reminder of how to do these problems. So I just put in a variety of problems from really, really easy to something you go, oh yeah, that's right. How do we do this? Okay. So starting in our upper left-hand corner, the easiest of all problems. So all we're going to do here is we just need to combine our constants. So I am going to bring the 4 over to the right-hand side, and that, of course, will give me x equals 9. So this is just a really easy reminder. Whatever you do to the left-hand side, make sure you do to the right-hand side and vice versa. All right, so let's go ahead and go on to our second one. The easy ones sometimes are a little boring. Okay, so just a reminder about parentheses. So for this one, to get the x out, we cannot just subtract 2 from both sides because we have parentheses, so we have to deal with this 3 first. Now, there are a couple of different ways to do this. You can either distribute this 3 or divide both sides by 3. It really doesn't matter. For this one, let's distribute the 3 first. This is also why oftentimes in chemistry or any class that has math in it, your way of doing the problem might be a little bit different from the person sitting next to you, and that's fine as long as you get to the same answer. So in algebra, there are just so many different ways to go about this. Okay, so we're going to move this 6 over to the right-hand side. And of course, this gives us x equals 2, but you get the same answer if you divided both sides by 3. Okay, on to the upper right. So for this one, what I wanted to introduce was having like terms here. So you can see I have 2 terms with the x variable. Now, when you're combining like terms, you need to make sure that they are like terms. So because these both have an x and it's not like an x squared or an x cubed or anything like that, they are like terms. Of course, my constants are like terms as well. So I'm really combining like terms on both ends at this point. Okay, so what I'm going to do for this one is I think the easiest thing is to actually subtract 2x from both sides because that is going to give us an x on the right-hand side, and that means I'm going to add 8 to both sides, which just gives us 12 equals x. So that one was actually really easy. But the main thing I found with combining like terms is just make sure you have true like terms. Okay, so going on to the lower right, this one here, again, we're going to have some like terms, but we've got parentheses. So you have to make sure you're dealing with things in the correct order here. So what I'm going to do with this one, I could like divide both sides by 4 or 5, but that's going to make things kind of messy. I think the easiest thing to do here is what we did in this one as well. And that's just distribute this 5 through this parentheses and also distribute the 4 here. Okay, so this is going to be 10x plus 5 and 20x minus 8. And I'm going to find my like terms, and my constants are also like. And let's keep this positive. So I think I'm going to subtract 10x from both sides. Okay, so that's going to give me a 10x on the right. And that means I'm going to go plus 8 here. So that's going to give me 13. And then divide both sides by 10. So that gives me x over here. And this is going to be 13 over 10, which is also 1.3. Okay. Also, again, you can kind of write this however you want. Sometimes when I get to this point, even though I've taken my x over to the right-hand side, you can always flip this, because a lot of times we like to put the variable alone on the left-hand side. So that's a habit that a lot of people have, including me, but you don't have to, like this one up here. I put the x on the right. It's totally fine. It's absolutely equivalent. You write it however it makes the most sense to you. Okay, let's just make sure, good, we've got no questions there. Again, hopefully these are easy, and this is just a really kind of quick review of like, oh yeah, I remember that rule for doing this algebra. Okay, so these are still just one variable equations, but I wanted to do something that was just a little more complex here. So let's take this one in the upper left first. Again, because I've got a fraction, I actually don't want to do any dividing or multiplying by the inverse. I think the easiest thing to do is to distribute again. However it makes sense to you, you can do it however you want, but let's distribute their 3/4 and let's distribute the 7 there. Okay, so I am going to multiply this 3/4 by 2x. I'm actually just going to call that 6/4 x. So the nice thing is, when you're kind of working these problems on your own, you don't have to worry about having an improper fraction or like this fraction is totally not reduced. It's absolutely fine. It doesn't make a difference. You work it however you want to. 3/4, that's going to be minus 6. And then we're going to have 7 times 1/2. Again, I'm going to keep that an improper fraction, but you don't have to. And then this is going to be 42. So again, I've got 2 x terms and 2 constants, so I need to combine this. So I think if I subtract it, yeah, this is going to give me 2x on this side, and I'm going to have negative 48. Great, so divide both sides by 2, and I'll just keep the x over here, so that'll give me a negative 24 there. Okay, again, hopefully this is easy. This is just kind of remembering how all these little algebra rules work. Now, I did specifically want to do both of these equations because these type of equations you run into when you do gas laws, especially if you do combined gas law. So the first one that I want to start with is actually this one on the lower left because it's a little bit easier. So you have the x in the numerator. So again, you've got multiple options here on what you want to do. But when I have 2 fractions set equal to each other, I think the easiest thing to do is to cross multiply. So that means I'm going to multiply these 2 terms. Let me change color. And then I'm going to multiply these 2 terms, and those equal each other. And I'll show you what I mean. So this simplifies, let's see, I did do this. We get some rather big numbers here. X is equal to 747. And then the x is much easier to solve for. Of course, I'm just going to divide both sides by 704, and I get x is equal to 1.06. And this cross multiplication technique works really, really well if you look in this upper right-hand corner problem. So these tend to throw students more for a loop because the variable is in the denominator. So if you're if you're solving these and the variables in the denominator and you're trying to do it by either multiplying both sides by something or dividing both sides by something, then sometimes you get things flipped and you'll end up with a reciprocal as an answer. So again, this is where I like to cross multiply because it brings your variable, in this case your x, to the numerator, and you don't have to worry about making sure things are in the right place because they just get to the right place automatically. And again, I did this calculation, so that's 288x is equal to 75, and then x is equal to 0.26. Again, that's really handy when you do gas laws, especially combined gas law. You'll find that a lot. Cross multiplication is definitely your friend. Okay, so those are our easy solving linear equations. One variable. Let's make sure there are no questions. There are no questions. That's fantastic. I didn't expect too many questions on that. Let's go on to now still linear equations, but we're going to do two variables. So this is specifically actually where I want to talk about graphing because we're going to have an x and a y. So just again to review the very basics of graphing, you have, well, this is just 2D graphing. You have two axes. You have an x-axis here and a y-axis here, and you can plot points. These are called ordered pairs, so they have an x value and a y value. So this line here, actually this is, maybe I should write it here. This is the line y equals x. This is a really simple line, but characteristics of these lines is they will have a slope, and I've written the equation for the slope here. So this is how your y variable changes over how your x variable changes. Sometimes people call this as your rise over run, or your change in rise over your change in run, but we calculate the slope by knowing how the y values are changing over how the x values are changing. So for this graph here, you can, well, my tick marks are not totally in, but you can see if I started at 0, 0 and I went to 1, 1, my y value changes by 1 and my x value changes by 1. So my slope here for this is 1. Oh, the other thing I did want to point out about the graph is you have a y-intercept and an x-intercept. We do use the y-intercept more. So the y-intercept is where your graph of the line is going to cross your y-axis. Now for this line, it crosses at the origin or at 0, 0. So this is where your x value is going to equal 0. So again, in this case, where x equals 0, y also equals 0. Now, this is also true for the x-intercept. Again, this is where the line is going to cross the x-axis, which is, of course, is right here. And the nice thing about this line is it crosses both the x and the y-axis at the same point at the origin, 0, 0. But this is going to be where your y value is equal to 0. Now, in the next couple of slides, we're going to use the y-intercept much more than the x-intercept, but I thought I would just go ahead and throw both of them up there. Okay, so that's pretty much kind of a quick review on graphing. Let's talk a little bit more about how we write the equation for lines when we graph them. And this is very common in calibration curves, especially. You'll use this. But even in other things, you will find an equation for a line and you'll be able to derive different things, or you'll be able to figure out, especially if you've got a calibration curve, like what a concentration of an unknown is or something like that. There are a lot of different places that this tends to pop up. Okay. So the most common form that you'll see for lines is the slope-intercept form, and this is y equals mx plus b. Hopefully this looks familiar. So again, you have your y and your x. Those are your variables. You've got two variables because you have two axes. Your m here is your slope. Let me label these. Okay, so this one is slope. And your b is your y-intercept. Now, with slope-intercept form, we only need to worry about the y-intercept. We don't actually have the x-intercept. You can find it, but we're usually most interested in the y-intercept because getting the equation of the line in this form is just, it's a really easy way to work with it. Now, we don't always know what the y-intercept is, and we might not know what the slope is. So to get to the slope-intercept form, we'll very often use the point slope form. And what this does is it means if you know the slope and you know one point on the line, then you can figure out the equation of the line. Or if you know 2 points on the line, and we will practice this, if you know 2 points of the line, you can calculate slope and then use one of those points to find the equation of the line. And this, I feel like, just in chemistry is most common, that you will have 2 different points and then you're trying to derive the equation of the line. So again, your M here is slope, and your x1 and your y1 is your 1 point that you have, where this is the value for x from your 1 point, and this is the value of your y from your 1 point. Now, your x here and your y here, which are not x1 or y1, those just stay. X and y, those remain your variables, because again, we're trying to get something that looks like this: y equals mx plus b, with numbers plugged in for our slope and our y-intercept. So we have a problem here. So we want the slope-intercept form. Again, this is the most common form, and we have 2 different points. So I'm going to end up using the point slope form, but first I need to calculate my slope. And if you remember, my slope is simply my change in y over my change in x, or you can think of this as, say, y2 minus y1 over x2 minus x1. Now, the most common mistake I see when calculating slope, or when you have 2 points, is not keeping track of which one is x1 and y1 and which one is x2 and y2. So let's go ahead and just do this for this problem, and we can assign whatever we want here. So what if we called, let's kind of go crazy, and let's call this x2, y2, and then this would be x1, y1. Mostly just because I want a positive number on top. But you can do this however you want. So you can make this first point your x1 and your y1 if you want, and this second one your x2 and your y2. It doesn't make a difference. We will come to the same answer. Okay, so this means I'm going to do 3 minus 1, which is why I decided to make this one y2. And then I am going to take this over 1. Well, that's going to be negative anyway. Okay. So this is going to be 2 over negative 4, or we're going to have a slope of negative 1/2. So I didn't actually save myself a negative at all. Okay, so that is my slope. And then what I need to do is I need to choose one of the points and use my point slope form. And that is going to, when I simplify it, that is going to give me my slope intercept form. Okay, so let's just rewrite this equation first. And of course, you can use whichever point you want. It doesn't make a difference. Let's go ahead and use this point right here. So that's going to be y minus 3 is equal to negative 1/2 x minus 1. Okay, I'm just going to do my next step right here since I'm running out of space down below. So what I want to do here is I'm going to distribute. So again, we're using our skills that we just reviewed with just the really simple linear equations. So we'll keep this y minus 3, and I'm going to have negative 1/2 x, And this is going to be plus 1/2 because I have a negative times a negative. And then I need to combine my like terms. So I have two constants. Those need to be combined. I'm going to leave my y on the left-hand side. Again, I'm trying to get it like this, and I'm going to leave my x totally alone as well. So all I'm doing is I'm adding 3 to the other side. So this is going to be y equals -1. That one is kind of janky. Okay, 1/2 x. And then plus 3. And because we already have a 1/2, let's just make this 7/2. This 1/2 is kind of bothering me. So let me just fix that. That's much neater. Okay, so these 2 points have this equation of the line. Okay, good. Questions? All right. Good. No questions. Let's, on the next page, we're going to practice this just a couple more time with different points. All right. So again, because each of these, we have 2 points. Again, that's very common in chemistry that you're going to have a couple of points, and then you have to get the equation of the line, which is like why I'm practicing these. Let's get slope first here. All right. So again, my slope is my change in y over my change in x. And let's go -8 minus 8. I got to make sure I keep the signs in the right place. And this is 8 minus 9. So this is going to be -16 over 1, or a slope of -6. Oh, sorry. I dropped a negative here. This is -1. So that is just a slope of 16. All right. And now I have my point slope form. So let's go. Let's use this point. Well, no, changed my mind. Let's use the first point. Okay. So we're going to have y plus 8, because this is a -8, and this is going to equal 16, which is our slope, x minus 8, and now we just need to simplify. Okay, so I'm going to simplify over here. So this is going to be y plus 8 is equal to 16x. I think I did that calculation. Yes. Okay, so this is -128. And then I'm just going to combine my like terms here. I'm going to keep my y on the left. This is still 16x. And now this is -136. Okay, so that is the equation of the line for that one. Let's go on to the next one. Still same thing. Slope is change in y over change in x. And one thing you can do if you come back and you want to rework these problems is work them in the opposite way that I have worked them, and just make sure you get the same equation for the line. Okay, so let's go -3 minus 0, and that's going to be 6 minus 1. So that's going to be -3 over +5. Okay, so that's just -3/5. Maybe I'll rewrite it with the negative out front. Okay. And then we'll go again, point slope form. So I'll say y minus 0, just because that is going to be easy. And this is x minus 1. All right, so continuing on with my algebra over here to the right. So this is nice. This y minus 0 just goes straight to y. And I'm going to have -3/5 x plus 3/5. And that is my equation of the line. So it is generally nice when one of your points has at least 1 0, because it just tends to simplify things down. Okay, one more set of points. Again, we're just going to keep on doing the same thing. So hopefully after a while, these become very routine and very easy. And so that when you have to do a calibration curve like in lab, then you're the one that all your lab partners will go to find the equation of the line. Okay, we'll go, that's going to be plus 8. Okay, so that's going to be 14 over -2. Okay, it's going to simplify down to -7. Again, using point slope form, we have y minus 6. Our slope is -7. And that's going to change the sign. Okay, and let's just continue to simplify here. And that is going to be a -63, that x. And maybe I'll do squiggly lines. Let's just combine like terms so we can get y alone there. That is going to be -57. Okay, so that is our equation for the line. Okay, any questions? Nope, no questions. All right, great. So that's it for doing point slope form, and that is it for our linear equations. So now we're going to get into some more difficult equations. We are going to quadratics, and specifically we are going to be going to the quadratic equation itself. So a quadratic just means that you've got an equation with an x squared term. And these are, like parabolas will also be quadratic equations, but specifically we are generally wanting to solve for x. And you see these pop up very often when you do equilibrium problems, or if you're doing weak acids or weak bases, because those are also equilibrium problems. So you need to be able to solve for x. There are a couple of characteristics that I want to point out about quadratic equations. So first, quadratic equations, we generally write them in the form where you have your x squared term first, and then you write your x term, and then you have your constant. Now this a, b, and c are just the numbers in front of your x squared and your x, and of course c is just your constant. It doesn't have a variable with it. To use the quadratic equation, you need to make sure that your x squared equation looks like this with an equals 0 on the right-hand side. Otherwise, your quadratic equation right here is not going to work. So that is something I want to point out. The other thing I want to point out is because you have an x squared term, you are going to find two different solutions. Now, you can have two real solutions, what we call real roots. You can have repeating roots, and you can have imaginary or roots that are not real. Now, when we're doing chemistry problems, and you have like one real root and one imaginary root, or one negative root, you usually drop the negative root because you're looking for a positive answer there. Okay, so let's talk a little bit about the quadratic equation itself. Again, these letters here correspond with these letters here, which is why it's so important whenever you have a quadratic, before you apply the quadratic equation, make sure you get it in this form where you have ax squared plus bx plus c. Also, this term underneath here is called the discriminant, and it's nice to work out the discriminant first, or to calculate the discriminant first, because then you're going to know if you've got real roots, or if you've got a negative number over here, which is going to make imaginary roots, or even if you have repeating roots. So if this thing ends up being 0, it means your roots are repeating, which honestly does not happen very often, especially in chemistry. Okay, so we have a quadratic. It is already written in this form, so we just want to apply the quadratic equation, and we want to solve for x. Now, again, we're going to be looking for two roots here, and I'm going to do the discriminant first to figure out if we've got real roots or not. So let's go ahead and maybe for this first equation, I will specify what all of our numbers are. So a, again, is just the coefficient in front of the x squared. So a equals 2. B equals -7. Again, it's just right in front of the x. And remember, these are our pluses here. So this minus means that B is actually -7. And C, just like B, is -4. So all I'm going to do is I'm going to take these numbers and I'm going to plug in. Again, I'm going to do the discriminant first because that will give me some information about my roots, but you don't have to do that. You can just plug everything in and solve the equation, and that's totally fine. The one thing I will say again, if you're doing chemistry and you end up with something that has no real roots, then something has gone wrong with the calculation, and I would go back and look for some kind of mathematical error, because you should have at least one real root, especially if you're solving equilibrium problems. Okay, discriminant. So this is going to be b squared minus 4ac. So this is going to be a -7 squared minus 4 times 2 times -4. And I have done this calculation, and that gives me 81. It is a positive number, so I'm going to have 2 real roots. So yes. Now I'm going to go for the big quadratic equation. So I'm going to have x equals 7, because remember it's the opposite, or -b, and this is going to be plus or minus the square root of 81 over 2 times a, which is also 2. Okay, so continuing, I'm just going to continue on here. I'm going to have x equals 7. We'll do the plus first, plus the square root of 81 over 4. Again, I just multiply 2 plus 2. And also we have our second root, which is 7 minus the square root of 81 over 4. And maybe I should have already made that 9, but it's too late. It's not a problem. Okay, so we're going to have 7 plus 9 over 4, and x equals 7 minus 9 over 4. So again, you can see I've got 2 real roots. This is going to give me x equals 4, and I did this one as well. This gives me x equals -1/2. So those are my solutions to this quadratic. And again, if I was working an equilibrium problem and you have to choose one, you would choose the positive root, not the negative root, because you're never going to have a negative concentration. That does not happen. Okay, so we're just going to keep practicing some of these, because just like anything, the more you practice it, the more routine it becomes. The easier it is when you see this, again, either in lab or in a homework, or of course on a test. You want it to be very, very routine. So I'm going to start here on the left, and I'll go ahead and write everything out. So a equals 1, b equals 1, and c equals -240 for this equation here. So I'm going to do the discriminant first. So this is going to be 1 squared minus 4 times 1 times -240. All right, and that gives me a discriminant of 961. Now, the nice thing is that actually is a perfect square. But let's go ahead and write our roots out. So we've got x is equal to -1 plus or minus the square root of 961 over 2 times 1. So I think this time I'm going to actually simplify it first before I break it into 2 roots. So this is going to be -1. So yes, this is actually a perfect square. It's the perfect square of 31 over 2. So now I can do my 2 roots. So this is going to be -1 plus 31 over 2, and x equals -1 minus 31 over 2. And I get these to resolve to be 15 and -16. All right, let's keep going. Let's do this one right here. Okay, again, so I'll write down a equals 1, b equals 3, and c equals -4. So discriminant first. This is going to be 3 squared minus 4 times 1 times -4, and that equals 25, which is another perfect square. So now let's write down what x equals. Okay, so this is going to be -3 plus or minus the square root of 25 over 2 times a, which is 1. So let's simplify a little bit. So -3 plus or minus 5 over 2. All right, so now here are my two values for x. I'm going to have -3 plus 5 over 2, and x equals -3 minus 5 over 2. And that is going to give me x equals 1 and x equals -4. Okay, so that is how to solve quadratics. The other thing that you can do, again, I'm thinking equilibrium problems, is sometimes these numbers. So these examples that we've worked with really nice whole numbers, and we've worked with perfect squares, and it's worked really nicely. If your professor allows it, you can program your calculator to run the quadratic equation, although some calculators come with it already programmed on. So that is another thing that you can do. Just make sure that it is in this form here, and that you have the correct values for A, B, and C before you run it in your calculator. It's really handy to have in your calculator, especially if you're dealing with really tiny or really large numbers. But again, getting it into that proper form is really critical because the program is only as good as the numbers that you put in. Okay, so those are our quadratics, and now we get to talk about logarithms. This is something that usually gives students fits when they get into it. So the first thing that I want to actually establish about logarithms is logarithms are really just exponents. So you can see here I've written a general form of an exponent, and you can rewrite that as a logarithm. So here is it written as a logarithm. So you notice that this b here becomes the base of the logarithm. It's kind of why it's called b. Your y alone on the left-hand side of the equation becomes this number right here, and your exponent gets put off alone by itself to the right there. So you can do this with any exponent and or any logarithm. And then sometimes it makes it easier to solve for x. Not that we have to solve for x. I really just wanted to show you how these worked. So here is our exponent, and to write it as a logarithm, this 2 becomes our base. The 16 comes right next to the log, and our x was is in the exponent, and it sits right here. This one actually ends up being x equals 4, I believe. Okay, but again, the point here is not to solve for x. I just want to show how these exponents become logarithms. So when you think about logarithms, think about exponents. Again, we do the same thing. So this 3 here becomes the base of our log. Our 81 we put right here as the log base 3 of 81, and our exponent, is out here. And unless I'm much mistaken, I believe, yes, x equals 4 again. Okay. All right, so that's logarithms. Logarithms, exponents. Logarithms, exponents. Like, it helps to merge those concepts in your head. Now, in chemistry, we use log base 10, which is just log. So we don't very often, especially in general chemistry, use much natural log. So I'm not going to worry about that again in this review. I just want to set you up for general chemistry. But I want to make sure that I, again, make this connection between logarithms and exponents, because if you can make that connection, then you can understand how logarithms work. So I've just got a scale here, and lots of things that we measure are actually on a logarithmic scale, like the Richter scale is a logarithmic scale. So what I want you to first notice is, again, this is just a number line, 0 through 9, but I made it logarithmic. So notice how this 0 becomes the exponent. This 1 is the exponent. This 2 is the exponent. So you can see all of these numbers, like this 9, becomes the exponent. That's what makes it a logarithmic scale. So the interesting thing about this is let's look at the difference between, say, 4 and 6, and maybe I'll write here. So if you were just a linear scale, you would move up 2 spaces to get to 6. So 4 plus 2 equals 6. But if you're on a logarithmic scale, the change from 4 to 6 is you're going to multiply by 10 each time. So this is a difference, let's say, from 4 to 6 is actually a difference of 100, or you can think of it as 10 squared. So there's your 2 that you want to go up 4, 5, 6, but it's a logarithmic, it's an exponent. Again, logarithms, exponents, logarithms, exponents. So this is why when you have earthquakes, the more you go up the scale, the more destructive it is. So like what would be the difference from, let's still work with 4. Let's say you had an earthquake at 4. So we'll go from 4 and let's take it up to 8. So if you were on a linear scale, then you'd want to say, oh, well, an earthquake that registers an 8 would be twice as destructive. But that is actually not true at all because you've got a logarithmic scale. So let me just... It's going to be much, much, much more destructive. So remember, each time you go up 1 on the logarithmic scale, you multiply by 10. So these each are 10. So the difference from an earthquake that's a 4 to an earthquake that's an 8 is 10 times 10 times 10 times 10. This is a difference of 10 to the 4th. Again, there are 1, 2, 3, 4 tens there. Or you can see this is 10 to the 4th to 10 to the 8th. And that is actually a difference in strength of 10,000. So these logarithmic scales are really important to understand how they work because we all want to make everything very linear. We're used to working with things that are linear, but remember, logarithms are exponents. Okay, so that's just general logarithmic scale, and I am going to add the twist that comes with chemistry. Okay. And when we deal with logarithms, most of the time we are dealing with pH, again, in general chemistry. So the way we calculate pH is I put the equation right up here. It is log, it's base 10, and we're looking at the concentration of hydronium, or you can think of this as the concentration of H+, which is why we call this pH. This is an inverse logarithmic scale. It works very, very similar, but the thing that I want to point out is, so if you have a pH of 1, my red marker is not really showing up. So if you have a pH of 1, that corresponds to a concentration of 10 to the negative 1. If you have a pH of 6, it corresponds to a concentration of 10 to the negative 6. And you will notice as we move from left to right, as we move up in numbers on the scale from 0 to 14, our concentration gets smaller and smaller. Again, it's an inverse logarithmic scale. So if you want the highest concentration of hydronium ion on the pH scale, you want pHs that are very, 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 very low. So that's why we have acids down here from 0 to 7, and then these are bases up here because acids have a higher concentration of hydronium ion, but that's getting into a little more chemistry than I want to do. Again, it's the same idea. I want you to equate these numbers on the pH scale with the exponents here in the concentration. So let's work a few problems. Again, I'm going to keep our equation up here because that will help us. So what we want to know is, what is the pH if the concentration of hydronium is 1 times 10 to the negative 5th? The nice thing about this is just 1. It's 10 to the negative 5th. Again, if we think, okay, pH is a negative logarithmic scale, we actually don't have to plug anything into our calculators, although you can. It just means your pH here is 5. So I took my exponent and I took the negative value of that. Okay, so we can do this for anything that is 1 times 10 to the whatever. So if our concentration of hydronium is 10 to the negative ninth, our pH is simply 9. And the same thing here, this is still 1.0 times 10 to the negative second. Our pH is 2. So all that I've done is I put it in a little different form, but really, if I can go back, you can see I'm just pulling from this. Oops, I didn't mean to write on that. I'm pulling from this scale here. Just to, again, reiterate that this is a logarithmic scale, so we're looking at exponents. But of course, when we're calculating pH, we don't always have 1 here times 10 to the negative second. We usually have different things. So let's look at what happens if the pH is 2.5 times 10 to the negative third. Okay, so this one you are going to have to put in your calculator. So what we're going to put in the calculator is negative log of 2.5 times 10 to the negative third. Now I do have my calculator here, and I want to show you how to put this in. Because this concentration is in scientific notation, and it's really important when you're doing scientific notation in your calculator that you speak the language of your calculator ease. So let me first, I'm going to try to show this here. There it is. So you see this, little button here that has the double capital E. That gives you your scientific notation. It's really important that you use this button for scientific notation. So let me show you what it looks like when I put this equation that I wrote down into my calculator with the negative log. So this is 2.5 times 10 to the negative third. Okay, so I want to make sure that you guys can see this. So you see how you get that little e out, and make sure you close your parentheses. That tells the calculator that this is a single number and it's just in scientific notation. Now, if you're really careful with your parentheses, you can use the times 10 up caret negative 3. But what I have found is students don't consistently use the parentheses correctly, because you have to be so picky with these parentheses. And also, I like to save keystrokes. So the fact that I can put scientific notation in with just this E also helps save me keystrokes, which I like to do as well. Okay, so then I just press enter, and you can see I get, let me see if this shows up. Yes, I get the answer right here. So that is 2.6. So we will write our answer. Our pH is equal to 2.6. There's also a little bit of a logic check here. While you can't just take the exponent down, your answer should be close to what the negative exponent is. So if this was 1.0 times 10 to the negative third, I would expect a pH of 3. And so the fact that I am close to 3 gives me confidence that, yes, I have done this calculation correctly. This makes sense. So if you get a pH that, say, is negative, or like it's 13 from this concentration, hopefully you have red flags that start waving to say, no, wait, this doesn't make sense. If I have an exponent of negative 3, then my pH should be somewhere around 3, maybe a little under, maybe a little over, but somewhere around 3. Okay, let's do this next one. And again, I'll show you how I put it in the calculator. Okay, so I'm just going to do the negative log of 3.021 times 10 to the negative fifth. So when I put this in my calculator, again, I'm going to use my little e to tell the calculator that I'm doing scientific notation. So let's make sure that you can see it there. Okay, and then when I hit enter, I get my answer right there. And so that is a pH, what was that, 4.5. 4.5. Actually, I should probably have at least one more sig fig in there. I'm not getting very particular sig figs for these problems. Okay, So that is how we're going to calculate pH when we don't have a 1.0 here. But again, it should be close. So you can see my exponent is -5 and my pH here is close-ish to 5. I don't have something really off from that. Okay, so the other thing that I do want to cover is you don't always want to find the pH. Sometimes you have the pH and you want to find the concentration of hydronium ion. So what you want to do there is you want to do an inverse log. So all I've done for this equation here is I've taken my original one, and instead of having it solved for pH, I solved it for concentration. So what I did was I took the inverse of the log, which is an exponent. Again, logarithms, exponents. So if I want to solve for my concentration of hydronium, I'm going to do 10 raised to the negative pH. And it's 10 here because it's log base 10. So that is where that 10 comes from. Now, the first couple of problems that we're going to run here, we're going to go really, really easy. So I have a pH just straight up of 8, no decimal points, no nothing. That means that I can basically just think about that pH scale and how the numbers correspond to the concentration. And so my concentration of hydronium is simply going to be 1.0 times 10 to the negative 8. Again, if I go back, there we go. So if I have pH of 8, there's my concentration. So again, I just want to show that connection. If you have a pH that is a whole number, then you just make that the exponent and take the negative. So again, if I have my pH that is 13 exactly, then my concentration of hydronium, I'm just going to take the negative of it, and it's 10 to the negative 13th. Okay, so those are the easy ones. Now let's do the more difficult one. And again, I'm going to show you what this looks like when you put it into your calculator. Okay, so again, I have the pH. I want the concentration. So my concentration of hydronium, this one is not going to work out easily. It's just going to be 10 to the negative 6.75. Again, I'll show you how that looks. The nice thing about this is you don't have to worry about scientific notation. Well, not for these problems. Okay, so I'll make sure my calculator. So that is what it looks like. You can see I just used the up caret, but make sure you get that negative in there. And again, if you're not sure where the negative is, it's right down there. And so when I hit equals, I get a concentration of 1.78 times 10 to the negative 7th. Again, I should see a correlation between my pH and my exponent. They should be close-ish. And you can see I've got a negative 7 here, and my pH was 6.75. So again, close-ish. They're not going to be exact, but they should be in the same ballpark. And for our last problem here, again, if I want concentration, this is going to be 10 to the negative 11.32. And I will put it in my calculator so you can see what it looks like. 11.32. Make sure you can see it. There you go. Notice I do use parentheses around it just to make sure that nothing goes wonky. Okay, and when I hit enter, let's see, I get a concentration of 4.79 times 10 to the negative 12th, which does make sense because my pH is 11.32 and this is 12. Again, close-ish. This is not raising any red flags for me. Okay, so those are, again, your very basic math skills. Hopefully most of this was review. I do find that students seem to struggle the most with the logarithms and working with pH and doing the inverse and all of that. So hopefully that helped clarify that. And thanks so much for joining us for the live stream. If you have any requests for topics that you want me to cover, just you can leave a comment in YouTube, or you can go to our Facebook page and leave a comment, or you can also email me, Karen@chemhelpasap.com. All that information is in the description box below. So I hope you enjoy the rest of your Wednesday. And again, thanks so much for joining us here. Good night.